Alright, so now let's talk about the Arrhenius equation. And this equation is used more specifically towards finding our activation energy. And this is just one form of the Arrhenius equation, where we have our K, which we obviously know as our rate constant. This A over here is our exponential factor, or I think pre-exponential factor, something like that. EA is our activation energy. R is our universal gas constant. But you really don't have to know that because our R is just going to be 8.314, and that should be joules over moles times Kelvin. So that's our R. Actually, let me write this a little bit better. So I'll write 3 right there. That's our R. And our temperature, which is going to be in Kelvin, most of the part, since our universal gas constant is in Kelvin or K. So that's what one form of our Arrhenius equation looks like. Now another form would be something like this, where when you do all the math, all the integration, whatnot, which I'm not going to be going through because honestly I really don't know how to do that. I only know the equations and how to use them. And over here we'd have our K1 over K2, and this should equal activation energy over our universal gas constant, or R, and that's 1 over T2 minus 1 over T1, T being temperature. And that's one of the forms of finding your activation energy given 2 rate constants and 2 temperatures. Now there's also another way of writing this through our y equals mx plus b format, and I'll say it again, I really don't know how to get through these calculations, like deriving all those equations and stuff. I only know that there are these specific equations, and if you're given these in your formula sheet, then great, but if not, then more than likely you're going to have to memorize it. So it's going to be ln of k equals negative of our activation energy over R times 1 over temperature plus ln of A, and this replicates our y equals mx plus b. And we're actually going to look at a graph showing what this sort of equation looks like. But these are the main equations you need to know. So it's just these 3 that you need to know. So I'll just put need. These are the 3 you need to know. More than likely you're going to get this in your formula sheet, and also this one. Maybe not this one, so maybe memorize this equation over here. But that is the Arrhenius equation. And now let's look at a plot of our Arrhenius equation, or our ln k versus 1 over temperature. Now, one of the biggest things to look at is our y equals mx plus b format. So I'm just going to change the font over here, and this part right here. This slope is equal to negative activation energy over R. So if you were given this graph, you could solve the activation energy pretty easily. So let's just write it over here. So negative 4,664.5 equals negative activation energy over R. And this is going to be in joules. So we multiply our R, multiply our R, which is just going to be 8.314 times negative 4,664.5. That should get us negative 38780.653. But this is in joules. Oh, and we could actually divide that negative over, so it would be negative times negative, so that should be positive. And this is in joules. Now, just to make it a little bit more pretty, we have our activation energy in kilojoules. So if we divide this by 1,000, we get 38.8. So our activation energy is going to equal 38, or actually, let me write this a little bit better, 38.8 kilojoules. So just how we got there, we multiplied our R, and I was a little bit too lazy to write 8.314, but we just multiplied our R's to get our activation energy in joules, or actually I should take this negative out of the way because we moved that negative. And we have our activation energy in joules. So just to make it look a little bit more pretty, we divided by 1000 to get to kilojoules, and that's how we have our activation energy being 38.8 kilojoules. Now over here on that same graph is our ln of A. So this will equal ln A. So our, I think it's pre-exponential factor, I'm just going to call it A. So if we wanted to find our A, all we really have to do is, since this is ln A equals 18.626, I think that was a plus, so plus 18.626. So all we have to do is raise it to the power of E. So when we raise it to the power of E, that's just going to be A equals E to the power of 18.626. And I'm losing room over here, but it's E to the 18.626. And you get a pretty wild number. Let me see how I can sort of summarize this. So it's 1, 2, 3, 4, 5, 6, 7, 8. So I got 1.2 times 10 to the 8th power. I think that's correct. Let me double check. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So 1.2 times 10 to the 8th power, and that is our A. So our A equals that over there, and that is how you can find your activation energy and even your A given a graph. Alright, so let's look at an activation energy problem using the Arrhenius equation. So it states that find the new rate constant at 310 Kelvin. So Kelvin is an important part of our Arrhenius equation, and it says rate constant is 7. This is second order because it's m to the negative 1 times s to the negative 1. I don't think we need to know that, but it's just something excess to know, and it's good to know that those specific units correlate to second order. So it's good to know that in the back of your head. And it's at 370 Kelvin, so that's our temperature for that rate constant. And then it says the activation energy is 900 kilojoules per mole. So all of that information is very useful. And the equation that we can use is this one right here. So it's ln of K1 over K2 parentheses equals our activation energy over our universal gas constant. That's 1 over temperature 2 minus 1 over temperature 1. Temperature 2 correlating to a rate constant 2. Temperature 1 correlating to rate constant 1. So we have this equation right here, and we already have our values. We already have the rate constant and this Kelvin right here, but we're looking for a new rate constant. So just to make this a little bit more easier in terms of the math side, I'm going to say that this new rate constant is going to be K1, and that means our temperature is going to be T1. So let's just plug in all of our values. So we're going to have ln, and I'm just going to have that K1 be x over K2, or no, not K2, 7, and I could put my units if I wanted to, but M and S would be over here. And for the activation energy, it's in kilojoules, but our universal gas constant is in joules. So we could go one of two ways. We could convert the kilojoules to joules of the activation energy, or we can convert the joules from the universal gas constant to kilojoules. Now I'm going to convert this 900 kilojoules to joules, so this would be 900,000 joules per mole over our universal gas constant is 8.314 joules per mole Kelvin. And I'll just put my units over here. So I think this is m times s, since this is m to the negative 1 times s to the negative 1. So I believe it's supposed to go up here. And once we know that, it's 1 over T2. So T2 correlates to our rate constant of K2. So that would be 370 Kelvin, 370 Kelvin minus, and then that T1, we're given the temperature. We're not given the rate constant, which we're trying to find. So it'd be 1 over 310 Kelvin. And we could just go from there, which we're trying to find X. So I'm going to try to solve this portion right here, just plugging that into my calculator. So let's see, that'll be 900,000 over 8.314, and then times 1 over 370 minus 1 over 310. So I get negative 56.62, and I'm just going to round this up to the third decimal place, 7. So that's my answer over here, and that'll equal ln of x over 7. So just to make it easier, I'm just going to take out all the units. So we just have numbers, and it just looks a little bit more easier. So to take out this natural log, we need to put it to the power of e. So putting to the power of e for both of those, and this will just cancel out, leaving us x over 7, and that should equal, and then for that e over there, we just plug it into our calculator, and that gets us 2.55, and I'm rounding here, times 10 to the negative 25. So multiply by 7, we get 1.788 times 10 to the negative 24 is our rate constant at K1. So we just found our rate constant, and if we wanted to double check, let me go down here a little. If we wanted to double check, we go back to our formula, which is ln of K1 over K2, and that equals activation energy over R, and 1 over T2 minus 1 over T1. Well, we really don't have to solve this again because we already know it's going to equal negative 56.65. So all we really have to do is see if ln, let me scroll down a little bit here. So ln of 1.788 times 10 to the negative 24 over 7, we need to see if that equals negative 56.627 in order for our answer to be correct. So once we do that, that over 7, and indeed we get negative 56.62, and if I round up 7. So that's when we know our rate constant is correct. Now, another thing you could have done is, and this would have actually been easier, is just 1.788 times 10 to the negative 24 over 7, and that should equal this. So if I did that as well, I indeed get 2.55 times 10 to the negative 25. Just checking my answer to see if that is my rate constant. So this is our answer. 1.788 times 10 to the negative 24, and actually, I think our units would be m to the negative 1 times s to the negative 1. So always put your units, remember that. But this is our answer for the question. 1.788 times 10 to the negative 24, m to the negative power times s to the negative power.